Particles don't actually have positions. That sounds strange, because in everyday life, everything has a position. If I throw a ball, I can point to exactly where it is at any moment. So it feels obvious that a particle, like an electron, should also have a definite location. But in quantum mechanics, that idea completely breaks down. To find out, let's start with how we originally thought about particles. Classically, a particle is just a point. It has a definite position and a definite momentum. And together, these completely describe its state. If you know both where it is and how it's moving, you can predict everything about what it will do next. This is how physics worked for centuries. But at very small scales, this picture stops working. At the quantum level, there's a fundamental limit to what you can know. You cannot know both the position and momentum of a particle exactly. The more precisely you know where it is, the less precisely you can know about how it's moving. And this isn't because our measurements are bad or flawed. This is a fundamental property of nature itself. So already, the classical picture starts to break. You can't describe a particle with a single exact position and momentum anymore. So if particles aren't just points, what are they instead? The answer is, particles aren't points at all. Instead, they're described by something called a wavefunction. The wavefunction doesn't tell you exactly where the particle is. It tells you the probability of finding it at different positions. If you take the square of the wavefunction, that gives you the probability distribution. So instead of a single point, the particle is spread out. Some locations are more likely and others are less likely. But there is no exact position until you actually measure it. And this idea leads to something really interesting when we start combining waves. Particles can be described by different kinds of wave functions. On the left, we have a localized wave. This is concentrated in one region, so the position is relatively well defined. But because it's made from many different wavelengths, the momentum is uncertain. On the right, we have a plane wave. This extends across all space, so the position is completely uncertain. But it has a single wavelength, which means the momentum is well defined. So you can't have both. If you localize the particle, you lose certainty in the momentum. If you define the momentum, you lose certainty in position. This is exactly what the uncertainty principle was telling us earlier. So how do we actually get a localized particle from waves? We do it by adding wave functions together. Each of these waves has a different wavelength or momentum. And when you combine them, they interfere. In some places, the waves add together, and in others, they cancel out. This creates a localized wave, something that's concentrated in one region of space. But here's the key idea. When you add wave functions, the probabilities don't just add. Instead, you get extra terms from interference. That's why you see this additional term in the bottom right equation. So the probability depends not just on each wave individually, but also how they overlap. And this interference is what allows a particle to be localized in the first place. So, in the end, particles don't have exact positions. They're described by wave functions. Those wave functions give probabilities, not definite locations. And when you measure the particle, you get a single outcome. But before that measurement, the particle isn't at one place. It's spread out as a probability distribution. That's what quantum mechanics really tells us.